The Polish Foundation for the Advancement of Science and the State Atomic Energy Agency present Secrets of the Atom, Dubna on the Volga. For centuries, people living in harmony with nature accepted its gifts and bore the hardships of everyday existence. The cold of winter, the heat of summer, the rains of autumn, with equal humility. All the same, they were forever plagued by recurring simple questions. How does it happen that the clouds float through the air and the trees turn green in spring? Their descendants wanted to know more. Could all of existence be reduced to the single element foreseen by Democritus, to the atom? But the atom also has its secrets. Those secrets are investigated by scientists from all over the world, working at various locations across our planet. One such place is Dubna, lying 120 kilometers north of Moscow, where the Moscow Canal joins the Volga River. It was here that the Joint Institute for Nuclear Research was set up in 1956. Currently, the institute has 7 laboratories which carry out various research and services. The first lab is the Laboratory of Nuclear Problems. Its most important piece of equipment is the so-called phasotron, which accelerates protons to the energy of 680 mega-electron volts. Moving on, we have the Bogolyubov Laboratory of Theoretical Physics, which maintains contacts with research institutes all over the world. The next lab is the Florov Laboratory of Nuclear Reactions, whose main piece of equipment is the 4-meter diameter synchrocyclotron, which is used to accelerate heavy ions. The next laboratory is the Laboratory of High Energies, which has the so-called nucleotron, which can accelerate nuclei to energies of up to 6 giga-electron volts per nucleon.
Oraz Laboratorium Techniki Obliczeniowej i Automatyzacji, stanowiące zaplecze komputerowe dla całego Instytutu.
During the spring 1994 meeting of the Institute's Scientific Council, Dr. Slava Furman introduced the project of a new piece of research equipment, the Intense Resonance Neutron Source, or IRON. It will produce impulses of neutron with the duration of 0.3 of a microsecond. Such short impulses allow for the neutron's energy determination to be based on the time of flight measurement. We will study both basic problems, such as breaking space and time symmetry, and applications suggested by research of excited states of nuclear matter. For the construction of IRON, we are using a lot of equipment from the already existing IBR post-neutron reactor, which allows us to lower the costs significantly. The neutron source's projected parameters will be comparable with those of the most modern equipment of this type in the world. My name is Yuri Alexandrovich Tumanov. I have been recording Dubna's life on film since 1961. I have been the head photographic engineer here for 33 years. 33 years. My son is 33 years old, and I have been here 33 years. I live in what you would have to call a very extraordinary city, very unique in every way. It is a city of scientists. Who decided to make it a city of scientists? This I don't know. It's hard to say because Dubna was established in 1956. The contract with the first scientist was signed on March the 26th. You know, I was very lucky. The first person I photographed was the first director of the Combined Institute, Dmitry Ivanovich Blokhintsev. Here's an artist. He paints. Once I had the good luck to photograph the academician Wechsler, the inventor of the synchrophasotron. An extraordinary man, really amazing. That's academician Bogolyubov. Professor Henryk Niewodniczański, Polish. I could go on showing the pictures I took over my 33 years here. I only photographed science. The thing is, there are no Poles here, no Russians, no Indians, Americans, Germans. There aren't any. Here there is only one nationality. We are all Dubnians. We have always strived to make Dubna more international. We had huge difficulties with that. After the collapse of the Soviet Union, however, we got our chance, and the number of member states has increased. We had 12 members because, China left, Cuba joined, Albania never participated. It was a founding member state, but it never sent a representative.
Albania nigdy nie brała udziału, bo ona się też była członkiem, krajem założycielskim Dubny.
I think the person who signed the agreement for Albania was the director of the Tirana power plant. He was their only expert. So we had 12 member states, but now, since Georgia, Azerbaijan, Armenia, Kazakhstan, Ukraine and Belarus, of course, since they also naturally became members, we have 18. Poland has been a member since the founding, since 1956, and Dubna's first Polish deputy director was Professor Marian Danisz, who started in '56. In the scientific council were very well-known Polish physicists. There was Professor Leopold Infeld, Professor Andrzej Sołtan, Professor Henryk Niewodniczański, and of course, Professor Marian Danisz. Waldemar Karcz was awarded a bonus for his work on multifragmentation, which contributed significantly to the whole Institute's research program. My name is Waldemar Karcz. I came from the Institute of Nuclear Physics in Krakow, and here in Dubna I work in the group of Professor Karnaukov at the Laboratory of Nuclear Problems, where we are working on a subject which you could say has become very fashionable in nuclear physics recently, that is on multifragmentation. The area is relatively new because it dates back to 1982 when Jacobson conducted the first experiment still using nuclear emulsions in which he observed this type of reaction. What is multifragmentation? Well, what happens is that a nucleus, which is bombarded with a heavy or light high-energy projectile, becomes excited, meaning it absorbs a high amount of energy and is able to fall apart into, let's say, its components or many different fragments. In other words, it is the opposite of what medieval alchemists were doing when they, for instance, tried to produce gold from many different elements. As I've said, multifragmentation is a disintegration, simply an explosion of the nucleus into many different pieces. Now, what are these pieces? They are simply different nuclei, ones which are lighter than gold. There's carbon, nitrogen, aluminum, silicon. So what we observe in our detector are various nuclei lighter than gold, such as, for instance, lithium, beryllium, boron. You've got the whole periodic table. With one important qualification, they all have atomic weight higher than 4, meaning they are heavier than the helium nucleus, and lower than 40, meaning about the atomic weight of calcium. Our cooperation with the Institute is limited to the following areas of research. neutron physics, using the neutrons from the IBR pulsed reactor to study the condensed phase. The second area is looking at processes under bombardment by heavy ions. Florov's laboratory has accelerators which accelerate heavy ions, and I must say that these accelerators have a very good reputation around the world, and which are probably the best equipment available to us, on which we can study reactions of heavy ions.
Bardzo dobrą markę na całym świecie. To są chyba najlepsze możliwości badania oddziaływań ciężkich jonów. No i wreszcie trzeci kierunek, już taki tradycyjny.
And finally, the third traditional area in which Polish physicists work is theory. Dubna has a large group of people working in the large theoretical physics laboratory, and Poles have been coming here to work with the excellent theoretical physicists.
Tutaj przyjeżdżają i współpracują z świetnymi teoretykami, którzy są na miejscu.
Currently, our laboratory is a theoretical physics institute employing about 60 professors and 90 PhDs. We have people from Egypt, France, India, and Germany working here. Germany is an associate member of the institute. We're also cooperating closely with scientists from Bulgaria, the Czech Republic, Slovakia, Poland, and so on. I came to Dubna, and initially I worked on light scattering in liquids. That was a continuation of the work I had done in Poznań. But recently I started working under or with Professor Jeromin on theoretical research of helium-4. Helium-4 as a system of interacting bosons.
Zająłem się teoretycznymi badaniami helu-4 jako układu bozonów oddziaływujących.
This is a very interesting area because there are some experimental results which have yet to be explained satisfactorily from the theoretical point of view.
Do tej pory niewytłumaczone jeszcze, nieopisane w sposób dostateczny, pełny teoretycznie.
Our laboratory is working in three broad areas. The first is fields and particles. We have 10 large units working in the most up-to-date areas of theoretical physics: particle phenomenology, field theory, gravitation theory, and so on and so on.
Феноменология частиц, теория поля, гравитации и так дальше, и так дальше. Вторая большая тема – это тема...
The second broad area is nucleus theory, and the third is solid-state theory. We do a lot of work on so-called high-temperature superconductivity. This is a very popular area of research right now, and we are conducting this work in close cooperation with the Neutron Physics Laboratory. The BR2 reactor, the most important piece of the Neutron Physics Laboratory's equipment, is one of the most modern and best high-intensity neutron sources of its type in the world. What makes this reactor different from other stationary research reactors is the fact that it modulates the neutron beam with a mechanical device, the so-called mobile reflector.
Мы на реакторе используем для модуляции реактивности, для генерации мощных нейтронных импульсов механическое приспособление, так называемый подвижный отражатель. Подвижный отражатель.
The mobile reflector, placed outside the core of the reactor, turns at a constant speed, and when its blade is located near the active zone, it produces a particularly high-intensity impulse of neutrons, which are then channeled through horizontal channels, 14 of them, to 2 large experimental halls, where we conduct the experiments.
Больших экспериментальных зала на физические мишени.
Materia jest tak skomplikowana.
Matter is so complex that you have to see it in different lights, and neutron radiation allows us to look at it in a unique way.
Oddziaływują z jądrami atomowymi i obraz
Neutrons react with atomic nuclei, and the image seen using neutron radiation is totally different from that given by X-rays or electromagnetic radiation.
przez promieniowanie elektromagnetyczne. I jeżeli byśmy mogli,
If it were possible, if we were rich enough and had enough neutrons, I'm sure that looking at matter with neutron radiations would be much more popular because it's, how shall I say it, it gives us more information.
informacja tu jest bardziej dokładna i znacznie
This information is much more precise and allows us to see inside the micro world, to look at how atoms live, why they form given structures, how they give materials their specific properties.
materiału. Neutron jeszcze ma tą zaletę, że
The neutron has one more advantage in that it possesses magnetic moment. It's as if it were this tiny magnet, and neutron radiation allows us to see magnetic structures very clearly and precisely.
Эта лаборатория была создана для того, чтобы
The laboratory was set up to investigate nuclear reactions in very complex systems of heavy elements, much heavier than uranium.
системами значительно тяжелее, чем уран. Для этого
That was the reason for building all the accelerators and other equipment. The whole idea is to obtain nuclei which don't occur in nature, very heavy nuclei, ones which we call new elements, since they don't occur naturally.
очень много нейтронов, и ядра, которые очень тяжелые. То, что мы называем новые элементы, которых нет в природе. Другая проблема.
The next area is not new elements, but what we call new isotopes. For instance, when we take oxygen, which normally has 8 protons and 8 neutrons, and produce a form with 8 protons and 12 neutrons, 20 neutrons, or 22 neutrons.
Чтобы этот кислород имел 8 протонов и 12 нейтронов, 20 нейтронов, 22 нейтрона. И тогда у нас получается
We obtain an
необычная
extraordinary neutron-enriched substance. The properties and weight of those nuclei are simply amazing.
Этих ядер удивительные, размеры этих ядер удивительные. И теперь амбиция...
Right now, nuclear physicists are trying not only to produce such nuclei, but to form them into beams, accelerate them, and observe their reactions with so-called exotic partners.
Так называемыми экзотическими партнерами.
Zajmuję się chemią radiacyjną.
I work in radiation chemistry, meaning I look at the effects of ionizing radiation on matter. There are different types of ionizing radiation. There are X-rays, gamma rays, but what we have here are heavy ion beams. They have a very high density of ionization, so it's a completely different type of radiation, and unlike with the other types of radiation I mentioned, there are very many unique and yet to be explained phenomena encountered here.
Niedobadanych do końca. Są to również
This type of radiation could also be very useful for therapy because it allows the energy to be administered more selectively and precisely to the areas which we want to target.
zdegenerowanych, które chcemy, prawda, usunąć.
Мы имеем сейчас два направления.
Right now we have two basic areas of work. One is the purely basic research I talked about earlier, and the second is applied research, where we use our accelerators to create new materials, super-thin membranes, which are widely used in biology, medicine, and the electronic industry to obtain super-pure liquid and gaseous environments.
В медицине, в электронной промышленности для создания сверхчистых сред, газовых сред и жидких сред. Другое направление.
Another thing we do is we make very pure isotopes, pure both chemically and radiologically. These radioactive isotopes are so pure that they can be introduced into the human body in order to observe how they are metabolized.
Радиоактивные изотопы можно вводить в организм человека и исследовать метаболизм этого элемента в организме. Тем самым
So you see, there's more than one aspect to nuclear physics. Last year, the Nuclear Reactions Laboratory started using the VOB Phobos spectrometer, which was constructed by German, Polish, and Russian scientists. The device consists of 30 modules assembled according to the rule of a logarithmic detector. Next year, the Phobos detector will be augmented by a synchronous area consisting of 922 detectors. The mechanisms of these detectors will be designed at the Institute of Nuclear Physics in Krakow.
Das neue Detektorsystem ist im Institut für Kernphysik in Krakau entwickelt worden.
I believe that the Polish scientists are probably more important to this institute than the institute is to them, and that's significant. Unfortunately, I also believe that the Polish scientists still don't have sufficient influence on what's done in the institute, the way research is conducted, on the division of funds between investment and consumption, which is to say, between investment and research.
Konsumpcję, w sensie naukową konsumpcję, to znaczy na badania.
You frequently get the impression that all these expensive devices become an end in themselves, and that the constructors, and not the physicists, are becoming more important.
Laboratorium reakcji jądrowych.
The group, which is part of Professor Pieniążkiewicz's research department at the Laboratory of Nuclear Reactions, is working on designing and building the COMBAS magnetic analyzer. We have been working on this for some time now, and our results so far are shown on photographs, these illustrations, and computer programs. The way this separator works can be seen in this illustration. This, you can see, is a view from the top. This is a side view. You have these magnets and these thermonuclear pumps, which create a vacuum, since this beam can only be generated in a vacuum. At certain intervals, we haven't decided where yet, we will put in profile measurement gauges, which will allow us to see what is going on inside COMBAS.
Tak, żeby móc mieć pełny przegląd tego, co się dzieje w samym kompasie.
The console will perhaps be located where we are right now, and its operator will be able to direct and monitor the whole experiment. Well, that's fairly straightforward. The nucleotron is a superconducting synchrotron used to accelerate the nuclei of all the elements of the periodic table, including uranium, to a maximal energy of 6 giga-electron-volts per nucleon. It was designed and built entirely by the experts from the High Energies Laboratory. Most great modern particle accelerators consist of an accelerating ring and an injector, as well as channels through which the particles are transported to the experiment. What we have here is the same classical system. The synchrophasotron, the old accelerator ring, then underground, the new accelerator ring of the superconducting nucleotron, the common injector from which the beams can go into either the synchrophasotron or the nucleotron, to be accelerated in that ring and to be used in experiments. The accelerator is unique in that it uses superconducting magnets whose field is created by an iron core. These magnets enable us to have a very quick cycle of fluctuation of the magnetic field. There are only 3 superconducting accelerators in the world, one in America, one in Germany, and the third is our Russian nucleotron. It differs from the other 2 in that it has the most economical and fastest working superconducting magnets. I would like to say a few words about the Scientific Council meeting and its decisions. This was the 3rd Council meeting at which we had not only representatives of member countries, but also people from the West. As far as the most important decisions go, first of all, it decided to complete the building and start up the nucleotron, which, as you know, already exists and works, but is not yet, well, fully operational. The second important decision was to undertake the reconstruction of the IBR-2 pulsed reactor and to make additional measuring devices to be installed in the reactor after the reconstruction. We also went over the results of the Laboratory of Nuclear Reactions. The thing is to remake the Phobos detector, which right now is a 2-pi detector, into a 4-pi detector, and to quickly install that Argus detector, which is in front.
Żeby stał się detektorem 4pi i żeby ten detektor na froncie, detektor Argus, też był szybko zainstalowany.
We spent a lot of time talking about the new device planned for the neutron physics laboratory, the IRON. We decided to install it in 1997 and to prepare a program of research which would use this resonance neutron source.
przygotowany program badawczy, w którym to źródło rezonansowych neutronów będzie używane.
In addition, the Nuclear Reactions Laboratory has produced an exotic nucleus, helium-10. That's a nucleus with 2 protons and 8 neutrons, meaning it has a very high number of neutrons, and they also produced a double magic number nucleus. 50 protons, 50 neutrons. That is the only case of such a heavy magic number nucleus with equal numbers of protons and neutrons. We're optimistic about the future. Of course, the Institute's situation changed significantly in the late 80s. It has been operating according to the rules of the International Center for Basic Science. You have already heard about its history. It was established by a merger of 2 Soviet institutes in 1956 and initially was connected with the Eastern European Socialist Bloc. That bloc is gone, but the institute still exists because what brings people together here is their love of science and technology, and that love has proved to be stronger than the political motives for the institute's creation. I just want to tell you something of which you may not be aware of, meaning that physics here, I mean in Russia, is very advanced. One has to say that due to the high number of educated people, specialists, this country is a place where we can learn a lot, and that is why our work and cooperation with this country are so important.
Masa krytyczna umysłów.
That is why we plan to grow and develop to become a truly open international institute. And in spite of the fact that the last years have been hard economically, international cooperation in the institute has been growing during that period. We have strengthened our relations with France, Italy, the USA. Our relations and connections with Germany have also become considerably stronger and closer. Germany is an associate member of the Institute. It isn't a full member like Poland, Russia and other countries, but they have a very good, stable research program. Looking into the future, we would like to make sure of 2 things. The first is strengthening the Institute's scientific base, because that is what makes an institute of this kind matter in the world. That is why we provide for the Institute's future, on the one hand, strengthening its base, and on the other, ensuring the recruitment of young workers, who are, of course, very important to our future development. That is why we have such an extensive education program. In connection with this program, we are planning to open a university based on the research center. We already have Polish students coming here. I believe that cooperation will grow. On the other hand, we will take the interests of our region and all our member states into account. I think that that's a good way to describe our perspectives.